Okay, so first of all, thank you for inviting me over to visit Ulsan. Great thanks to the main organizer, Rak-Kyeong. Rak was my PhD student in London, and I'm very proud of his achievements, and we keep on quite close contact since then, and it's nice to be here to visit and see his activities. So today I'm going to talk about new developments that we had for about 10 years, roughly, on the study of symplectic singularities. Those are geometric singularities which are important in physics constructions, but in addition, they are also quite important in the study of geometric singularities in mathematics and in the area of representation theory. So I'll try to give a general idea of what it is. Throughout the talk, you will see quivers like these. So those are graphs with some color codes and numbers that you see. Those should be thought of as combinatorial data for the construction of the particular singularity. If you're familiar with toric geometry, this is a similar construction, just like toric geometry contains combinatorial data for constructing a geometric singularity, then those graphs here contain geometric data for construction of symplectic singularities. The edges could have various types. They could be Dynkin diagrams, but they could be also extended Dynkin diagrams, as you could see here, if you're familiar with the topic of Dynkin diagrams. Okay. So I'll just summarize what we did in the past 10 years, and then I'll get into details if we have some time about that. So over the past 10 years, we faced an impressive progress in the understanding of theories with 8 supercharges. So for those of you who are not familiar, 8 supercharges is a way we use to encode a theory which has supersymmetry. In physics, supersymmetry is important because it allows to get, first of all, to get exact results, and second, to have particular structures, especially in geometry, which are restrictions of the geometry. We restrict the geometry, and then we get quite interesting singularities. So because of the success that we have, I would say starting from about 10 years ago, there was a communication with mathematicians, especially in the area of representation theory. Next week, actually, we will have Nakajima-san visiting from IPMU, and he will tell about the developments from the mathematical perspective. I'm a physicist, so I will tell the report about the progress from the point of view of a physicist. So this topic, the new topic that arises in mathematics is called the Coulomb branch. It's a new way of constructing geometric singularity. This previous techniques were called hyperkähler quotients. Those constructions begin to show up in the late 80s. And there is one important work by both physicists and mathematicians. Let me find this. Well, so let me just say it. The idea of a hyperkähler quotient was introduced in 87, I believe, by a combined work of physicists and mathematicians. The physicist is called Hitchin. Sorry, the mathematician is called Hitchin, and the physicists are Martin Rochet and Ulf Lindström. And they showed how constraints from supersymmetry lead to a very interesting geometric construction, which is known under the name of hyperkähler quotient. Since their work, which was introduced to both physicists and mathematicians, there was a lot of activity about construction of such moduli spaces, which are called hyperkähler moduli spaces, both in the case when they are compact and smooth, and also in cases where you have non-compact spaces and singular. So in physics terms, hyperkähler quotient is what physicists would call Higgs branches. And there was quite a bit of activity since their work about the construction of Higgs branches. But there were some issues with the constructions because they were only available for a particular type of singularities. So those which can admit a hyperkähler quotient construction. But with the years, we realized that there are many cases where hyperkähler quotient is not sufficient. And that's where we came up with this new way of constructing symplectic singularities, which is called the Coulomb branch. Okay. Now, we developed some tools to study those moduli spaces. And those tools were mostly coming from the physics area of gauge theories, supersymmetric gauge theories. That's my area of expertise, supersymmetric gauge theories. And many of those supersymmetric quivers, gauge theories are called the quivers. So they are represented by the graphs that we saw at the beginning. There are important objects in string theory which are called branes. And so many of those supersymmetric gauge theories that we study would show up on brane systems. And in particular, if we get into the details, we find that the names that we are giving to those theories are three-dimensional, so they live in 2 + 1 dimensions. They have 8 supercharges. That's called n = 4 supersymmetry. And again, the name that we give it to it in physics is a Coulomb branch. Now, the big development that led to all of this thing goes under a single formula, which is called the monopole formula. And I will show some aspects of this formula. This is the formula that mathematicians saw, and from there constructed this whole topic of a representation theory, which is called constructions of symplectic singularities using Coulomb branches. Now, I may have some time to talk about Hasse diagrams, which characterize those symplectic singularities, but this we will leave to the end, and we will see. And the rest of the comments are, we use this name magnetic quiver for the construction of many symplectic singularities, but we will see that. So in a physics term, the symplectic singularities is of great interest, because if I want to study a physical system, which could be either in 3, 4, 5, or 6 dimensions, then there was going to be a Higgs branch. And this Higgs branch would be a symplectic singularity. And the characterization of such a Higgs branch many times is given by quivers of the type that you see on the right over there. So on the right, we get a set of quivers that we encounter in our work. There is this column here where we see all of the affine Dynkin diagrams, or maybe it's more conventional to use the right column, where we see the classification of all affine Dynkin diagrams. They are ordered by those letters, A up to E. Those are simply laced affine Dynkin diagrams. And each one of them encodes a symplectic singularity. There's also the non-simply laced ones, the C that you see over here, and the B, which you see in this case. When we try to compute the moduli spaces associated to those Dynkin diagrams, we find that we get some interesting symplectic singularities. Okay. In mathematics, if you're familiar with the constructions of nilpotent orbits, then this is an area in algebra which are called nilpotent orbits. There are a collection of singularities which are called nilpotent orbits, and many of them have a realization in terms of quivers of the type that you see on the right. Another topic, which is a topic in representation theory, it's called affine Grassmannian. If we look at slices in the affine Grassmannian, those slices are symplectic singularities. So, to summarize, in physics, symplectic singularities show up as moduli spaces of vacuum configurations of certain theories, whereas in mathematics, symplectic singularities show up in various constructions, both in algebra and in representation theory. Well, there are some issues about names, but I will not go over that. Here's a diagram which shows the relations between the different types of symplectic singularities one can have. And so many of the symplectic singularities admit a hyperkähler quotient. This is the stuff which was known since the late 80s. And there's been a lot of activity on that, both in mathematics and in physics. There is the new construction, which goes under the name of Coulomb branches. Many singularities admit a construction using a Coulomb branch, but not as a Higgs branch, not as a hyperkähler quotient. However, if you do look at the intersection between those two, there are many singularities which admit a construction in both. And then there is a topic in physics which is called three-dimensional mirror symmetry, where it uses the connection between these two constructions. The way it is phrased in physics is that you have two theories where the Higgs branch of one is the Coulomb branch of the other, and vice versa. And there are many symplectic singularities which do not admit a Coulomb branch construction. They do not admit a hyperkähler quotient construction. They are yet to be understood in terms of new terms, possibly new constructions. For those which cannot be constructed as hyperkähler. So one, from the physics perspective, in five-dimensional theories, you have what you call instantons. And there is a way to construct a symplectic singularity by taking the set of all possible instantons dressed by dressing factors. So that's the space of dressed instanton operators. And for me, this is the best candidate to fill some of the gaps in over here. So we still don't understand how to construct moduli spaces of dressed instanton operators. But if we would understand that, it will be a nice completion of the diagram over here. Yeah, it will be similar in spirit to the notion of Coulomb branch as a space of dressed monopole operators. But it's much more difficult than with monopoles. And we can, once you discuss the details, you see the types of difficulties one encounters when trying to construct symplectic singularities as a space of dressed instanton operators. That's quite, yeah, it remains a big challenge to do that. And I can show simple examples, but this will require some technical details. Now, how do we understand symplectic singularities? There is a set of criteria that we use. And I list them here in the way of difficulty. So the simplest thing to characterize a symplectic singularity is to talk about the dimension. It's just a single integer number. And non-negative is the dimension of this symplectic singularity. And obviously, given such a dimension, there are many symplectic singularities. In fact, if the quaternionic dimension is 1, we have a classification of all possible symplectic singularities. This goes back to a work about 100 years ago, the work of Klein, Felix Klein, the mathematician. These are called Klein singularities, and those are just orbifolds of C2, AD classification of orbifolds of C2. Actually, another name which is mentioned in this context is Duval singularities. And so again, Duval goes back possibly 8 years ago. And those singularities, Klein-Duval singularities, are well known and are used in many areas, both in physics and in geometry and representation theory. Now, so if you try to go in dimension higher than 1, 2, or 3, there are no known classifications. It's a big challenge to try and classify singularities of higher dimensions. And at the moment, I don't see any way of trying to achieve this goal. But we move to the next way of characterizing a symplectic singularity. It's by the symmetry which acts on this space. So this is typically a continuous Lie group that rotates points on this space, acts on points, and moves from one point to another. And as a result, we could characterize holomorphic functions in terms of representations of those of the corresponding Lie algebras. So to find the symmetry of a symplectic singularity is non-trivial computation. Sometimes it's easy, sometimes it's more difficult. There are many issues to consider, but those are, in many cases, once we have the construction, either as a Higgs branch or as a Coulomb branch, the global symmetry is computable. Okay, next point in characterizing a symplectic singularity is to think about the Hasse diagram. So when we have a singularity, it could have some degenerations into sub spaces of the points. So if I have all of the set of points of the singularity, when I restrict to a subset of the points, I get a smaller singularity, and the structure of the smaller singularity is characterized into a diagram, a combinatorial diagram, which is called the Hasse diagram. And many times when we try to understand how complex the singularity is, what we do is to draw this Hasse diagram. By looking at Hasse diagrams of different singularities, we can compare one to another. So that's a third way of characterizing a symplectic singularity. It is relatively easy to compute, and therefore it's I put it third in order as the characterization of the symplectic singularity. Next thing that we can do is to look at the representation content. So the holomorphic functions on a symplectic singularity form a ring, the ring of holomorphic functions. And we could, as we mentioned before, if I have the symmetry, using the symmetry, the holomorphic functions would transform in representations of the symmetry. And now what I can do is to write down a generating function with all possible representations that show up for a symplectic singularity. This generating function is called Hilbert series. And it is next in line in the computations that we can do when we are characterizing a symplectic singularity. The difficulty in the computation could be quite high when we take a quiver of the types that we saw before, the graphs that we saw before, like those or those. If the numbers are high, then the computation becomes more difficult. So look down below. The numbers sum up to 30. And so that's quite a challenge to compute such a symplectic singularity. It has dimension 29 quaternionic. Next in line is the a concept which is called the generating function for highest weights of representation. It is equivalent to a computation of the Hilbert series, but it's slightly harder to compute. And I would put those two together in terms of complexity of computation. And then the last point that we use in order to characterize a symplectic singularity is what is known as the ring of functions. We take a collection, it's a finitely generated ring, so we take the generators of the ring and we explicitly write down the relations. This is the hardest of all, and we only do the computation of the explicit ring when it is absolutely necessary, let's say from the physics perspective, to have an explicit knowledge of the generators and the relations that they satisfy. So this summarizes what we are doing, and we develop tools to compute all of these concepts throughout the years. Okay. Next point that I would like to discuss is the quiver. So a graph like the one that we saw. Given such a graph, there are two moduli spaces I can compute. One is called the Higgs branch, or the well-known hyperkähler quotient. So that's the way which was described in late 80s. And there is the new way. The new way started showing up in physics literature in mid-90s. But it was, back then it was restricted, very much restricted to dimension 1. And most of the work back then was doing some guesswork and the fact that there is a classification in 1 dimension. So we look at the works from the 90s, and we found a restricted set of Coulomb branches. There was no real understanding of how to construct Coulomb branches, and so it stayed for quite some time, maybe order of 20 years. Now, both of those moduli spaces are symplectic singularities. There are some cases where Higgs branches are quite complicated. Instead of being a symplectic singularity, it's a union of several symplectic singularities. Or sometimes you have technical issues like normality of the moduli space. And this has been observed, but it's very difficult to study all of those points in detail because those are very difficult concepts. We are missing computational tools. And there is a notion of duality, which is called symplectic duality, which says that given a quiver, this duality relates the Coulomb branch of this quiver to the Higgs branch of the quiver. So we will not have time to describe what it is. Maybe I'll say in some words, in the physics terms. The symmetry of one, let's say the symmetry of the Coulomb branch, would be related to the space of deformations of the Higgs branch and vice versa. That's what symplectic duality. If we are looking at the theory, at the quiver from the perspective of a brane system, symplectic duality becomes a very natural duality. Yeah, so the name symplectic duality was proposed by a set of mathematicians, quite young mathematicians. This was done about 10 years ago. Back then, they did not know anything about Coulomb branch constructions of symplectic singularities, so they just looked at two quivers and hyperkähler quotients, hyperkähler quotient of one and hyperkähler quotient of another. They did not know about Coulomb branches and not about 3D mirror symmetry. Okay, yeah, so just to summarize, so for example, symplectic duality is one of the main points that got the attention of Ben Webster in studying the whole topic, and now he's, as a mathematician, he's thinking about Coulomb branches quite intensively. But there's not just him, there is a whole class of people which are studying representation theory, which are thinking about constructions of symplectic singularities using a Coulomb branch, because it's a very new construction. It's completely different from the construction of hyperkähler quotients, which was proposed in the late 80s. And as such, it presents many mathematical challenges in trying to understand the basic, not just the basic, but also the intricacies of the construction of singularities using Coulomb branches. Now, from the physics perspective, branes, which are extended objects in string theory, played a very critical role in the construction of symplectic singularities. So a brane system is something which is what we see here. This is some depiction of a simple brane system. The branes typically live in 10 dimensions, and since we are able to draw only in lower dimensions, this is a projection of the 10-dimensional system, in this case to a 2-dimensional subsystem. So it looks, the projection looks like what we see over here. There is this green line, which is very vaguely visible. So that's another object which shows up in the brane system. But using such rearrangements or an arrangement of branes in space-time, we are able to extract some combinatorial data, encode it in terms of the graphs that we saw, and get some information about the moduli space, either the Higgs branch or the Coulomb branch. Now, this perspective, which rose in string theory and not in mathematics, gave us quite a bit of intuition about computing moduli spaces, symplectic singularities, understanding the way they behave just by thinking about brain systems. And many times when I have mathematicians asking me, how did you get into such a result? My answer is that, I looked at the brain system. I can show you what I did, but it involves a lot of physics intuition, something that mathematicians who don't look at brain systems would not have. So really, the notion of brains played a significant role in getting many of the ideas that we understand today. Okay, I will skip this part. The only thing I will mention, this is the work of Hitchin, Karl Hede, Lindstrom, and Rocek from '87. It's a critical work in the development of construction of symplectic singularities. Back then, they did not even call it like that. They called it hyperkähler quotient. They were looking at mostly smooth manifolds, but they paved the way for the construction of many geometric singularities, which are known now today as symplectic singularities. Next are objects that we call magnetic quivers. So here's an example. So what we see here is the depiction of the weight lattice of G2, the exceptional algebra G2. It's a two-dimensional lattice because G2 has rank 2, and therefore it can be drawn on a two-dimensional sheet. Each point here is a weight in the weight lattice, and we assign a graph which is has the shape of the dinking diagram of G2 with some squares attached to it. These are called framings. So these are framed G2 dinking diagrams. Every graph contains 4 integers. Those are the 4 integers, and one can see the systematics of getting those numbers from the two-dimensional lattice. We also have, so there is a graph attached to each point on the lattice, and there are some edges connecting those points. Those edges are associated with roots of the G2 algebra. That's the root system. Actually, more precisely, it's a coroot. So we have those horizontal lines which are connecting. You see all of them have the same length. And then we have the slanted lines, those. And again, all of them have the same length. Those are the 2 simple roots. Yeah, so most of those lines are assigned with the letters which are the Klein singularities of type A. At the bottom, we see that there are a few exceptions, which actually lead to very interesting symplectic singularities, AG2 and CG2. Okay, so we have a collection of geometric singularities. In fact, one more comment about this graph is that I can assign a symplectic singularity to every pair of points in this graph. So I have infinitely many points. And given a pair, let's say I pick this one and this one, I look at the path. So to get from here to here, I need to use this line and then this line, A2 and A3. And I can associate a symplectic singularity, which will have quaternionic dimension 2, in passing from this point to this point. So I have infinitely many symplectic singularities, which are characterized by a choice of 2 points on this lattice, the top point and a lower point. And the Hasse diagram, or the phase structure of such singularities, is just given by the graph that we are seeing over here. Okay, now how much time do we have? Okay, so now I'm going to describe the way we got the breakthrough. So that's a work that we did in 2013. My collaborators are Stefano Cremonesi and Alberto Zaffaroni. Alberto is a long-time collaborator of mine from the previous millennium, and Stefano Cremonesi was a postdoctoral fellow with me when we did this work. So in detail, the construction of the Coulomb branch is such that we start from a Lagrangian. So that's a concept in quantum field theory. So there is a Lagrangian. Typically, it's characterized by the graphs that we saw. Yeah. Yeah, so that's one way of doing that. If you start with the, let's say, this graph here. So I have the numbers 8, 12, and 4. If I look at this subgraph over here, 8 and 4, so there is this technique which is called quiver subtraction that I did not mention today, but I suppose that whoever asked this is aware of this method. And so I could identify that 1, 4 is a subquiver. So I will write the transition to be of type A3, and then I will move to a different quiver, which is here. Sorry, it's this one, 7, 12. The 4 will be reduced to 2, and then because of the non-simply laced nature, I will have 3 on this side. So this quiver is what I will get by a quiver subtraction from this quiver of the quiver 1, 4. And so on. I can now continue. So from here, I'll have 2 transitions. There is an A2 transition for this subquiver here, and there is an A1 transition for this. So the 1, 2 now becomes 6, nothing here, and 6 here, and so on. So all of those quivers, I can start with the top guy and construct the diagram by applying quiver subtraction. When I reach this point over here, I would find that, so I no longer can use subtraction of A-type singularities, right? So that's the first point where there's no A-type singularity. And then I need to come up with new quivers. There are 3 new ones, AG2, CG2, and G2. So those are three exceptional slices in the Hasse diagram of the G2 affine Grassmannian. So I hope this answers the question. Well, as you can see, there are plenty of details one can talk about, but we only have 1 hour, so. But go on. If you have more questions, I'll be happy to answer. Okay, so one can ask, how come there was a time difference between the construction of hyperkähler quotients in late 80s and the final thing that we got back in 2013. I should say that it is this monopole formula that is mentioned over here that led mathematicians to, in particular, Nakajima-san, which will be here next week, to come up with a definition, a mathematical definition of the Coulomb branch, and then subsequently opening the whole field of study of Coulomb branches in the mathematical topic of representation theory. So they did see the Coulomb branches that were computed back in the mid-90s, but they couldn't figure out how to use it as a mathematical object and to generalize it to other cases. It was this monopole formula which was instrumental in the definition and subsequent study. Now let me explain what is this thing. So the monopole formula rose as a way to collect all of the data that we have of a Coulomb branch. The problem with the Coulomb branch is that it has many quantum corrections, and it was not understood how to encode all of the quantum corrections into a single computation. But this is what the monopole formula did, right? To collect all of the quantum corrections that a Coulomb branch admits, neatly encode them into a simple formula. And then once you have the formula, it allowed for computations of not just one Coulomb branch, but it's industrial production of many Coulomb branches. So it was really, if you look at papers before 2013, you'll see computations here and there of various Coulomb branches from a collection of techniques which are, each time they involve some trick, guesswork. But after this thing, you could see there are plenty of Coulomb branches which were just computed one after the other by this monopole formula. Okay, this we already saw, so I will skip that. Here's the monopole formula. So just general words, it computes the Hilbert series for the Coulomb branch of a 3D gauge theory with 8 supercharges. This we already made this comment. It just evaluates Coulomb branches on industrial scale. You just feed it into a computer, and you could take many graphs, and you get the Hilbert series for the moduli space. Once you have the Hilbert series, it's relatively easy to guess what kind of moduli space you have. Once you have the guess, then you could make some tests to see whether it's the right singularity or not. Yeah. I cannot hear. What do you say? What's the meaning of HT? Lambda? Yeah, so in order to evaluate the monopole formula, what I need, the input is a gauge group with some representation. And since it's a gauge group, it has a lattice, a weight lattice. The weight lattice typically is called the lambda. So if you're familiar with the theory of representations of Lie algebras, so lambda will be the weight lattice as opposed to the root lattice. And lambda hat, here there is a hat on top of it, is the dual lattice. So if we think of the lattice as the set of electric charges of the gauge group, then the dual lattice would be the set of magnetic charges that the gauge group can have. And here, when you have the sum, it's a sum over all possible magnetic charges that the gauge group can admit. And W is the Weil group of the corresponding algebra. So there is a natural action of the Weil group over the weight lattice and the co-weight lattice. And what we are doing here is to restrict to a particular chamber. It's called the principal Weil chamber. So I pick all of the co-weights or magnetic charges from the principal Weil chamber. That's what the sum means. And here there is a formula, delta. I don't believe I have an explicit formula for delta, but this is a piecewise linear function of a point on the lattice. And then Pm of t has an explicit form here, where di are the degrees of Casimir invariance of a Levy subgroup of the original gauge group, which is it's the by definition the Levy subgroup is the group which commutes with the point M on the co-weight lattice. So this requires some explanation and some technical computation. It's straightforward. It's all of those concepts are simple notions in the representation theory of Lie algebras. Any questions? Okay, so here's one of the comments that I said at the beginning, that when we study physical systems, many of them are characterized by hyperkähler quotients, but the more you get into details, you realize that there is a whole class of symplectic singularities which cannot be computed using a hyperkähler quotient. In the physics terms, it means that you have some gauge theory description, and you have a weak coupling regime and you have a strong coupling regime. At the weak coupling regime, you could use the techniques of hyperkähler quotients, but then those techniques fail as I move to strong coupling, and then I require something new. And this something new is what we called magnetic weavers. And this requires some techniques that were introduced that I will not demonstrate here, but just as a concept, it led to the necessity of constructing moduli spaces beyond hyperkähler quotients and then to the development of Coulomb branches as a technique. The main tool in computing this was through a brain system, but I will not go over this. Yeah, so I plan to go over the details of the monopole formula. We started doing it at the end of last lecture. Over there, you had just the abelian magnetic system. So the dual lattice is just a set of all possible integers. So if I have a U1 gauge theory, it has electric charges, which are parameterized by Z, right? So it's the set of all possible integer numbers. That's the electric lattice, but the dual lattice, the magnetic lattice, is again a set of integers. Now they parameterize the basic unit of magnetic charge and all possible integer products of such magnetic charge, right? So, and those are the things, those are the concepts that we need to think about. Every gauge theory has a set of electric charges, so those will be representations of Lie algebras, and there will be the dual, so weights and co-weights, or electric charges and magnetic charges. The dual lattice, which will characterize the set of magnetic charges.
For such a cover of class F theory, which one is easier to handle? Monopole formula versus
some cases it is easier to do the monopole formula. With whole Littlewood whole Littlewood expressions, mostly I found that whenever you have exceptional algebras, so if you take a class S where the algebra is of exceptional type, then that's where I refer to a whole Littlewood expression. Even though in practice, I'm not familiar with too many computations there, because it's quite a challenge to do that. No, there is an expression. So whole Littlewood polynomials are combinatorial objects introduced by Hall and Littlewood. And you could recast the monopole formula in terms of whole Littlewood polynomials. Now, the problem with the whole Littlewood polynomials is that to compute them, the definition is very easy. To actually compute them requires, well, just to give you an idea, what you do is you take a rational function, you take the orbit of this rational function under the Weyl group. Now, if the Weyl group of E6 has order 1 million, then that could be that you need to sum over 1 million rational functions. And so it becomes quite a challenge to compute it. And when you have a whole Littlewood formula, you take one weight, and for this there will be million terms. And then you need to go to the next weight, and for this there will be another 1 million terms. So it's quite challenging from the point of view of space. And actually collecting all of those terms together. And that's the reason that I've not seen too many computations in whole Littlewood expressions. I can show the expressions, and perhaps leave it as a challenge to those of you who are interested in coping with such difficulty. It would be quite interesting to get nice expressions for these things. More questions? Okay, I think we are done. Maybe since this is the talk for mathematicians, maybe it's good to mention the moduli space of instantons. So the instanton is the solution of a partial differential equation, the so-called self-dual Yang-Mills equation. It's a first order nonlinear equation. And if you look at all possible solutions to this equation, they form a space of solutions, and those are called the moduli space of instantons. It has nice properties. One very nice property is that the moduli space is a symplectic singularity. And there was a proposal by ADHM from quite some time ago for computing the moduli space of instantons, except that their proposal was to do it using a hyperkähler quotient, and they could only do it for classical gauge groups. So they couldn't do it for the exceptional types of G2, F4, and E. So for a long time, the construction of the moduli space of instantons for non-classical type was considered to be a challenge. So this is one of those cases where in physics, we knew how to construct moduli space of instantons, but only for classical type, but we didn't know anything about the exceptional type, and it remained a challenge for many years. And just because of the fact that for classical type, it admits a hyperkähler quotient. And actually, this was a motivation. How can you replace the hyperkähler quotient by something different and compute this symplectic singularity? And the solution was through this Coulomb branch. If you construct those moduli spaces of instantons using a Coulomb branch, there's no exception between the classical type and exceptional type. All of them look the same, look similar. They all admit the construction using graph, which are Dynkin diagrams. So here, this graph is the affine Dynkin diagram of type G2. And this graph here is the affine Dynkin diagram of type F4. This is the combinatorial data, and with this combinatorial data, I can compute the Coulomb branch, and the Coulomb branch will be the moduli space of K G2 instantons on C2. So this was a very elegant solution of the problem for computing a moduli space of instantons of exceptional type. And of course, the singularity was computed using the monopole formula. Here's another problem which shows up in 4 dimensions. People were trying to classify all theories which has rank 1, and they are leading to conformal field theories in 4 dimensions. And here's the list of the Higgs branch which come out of those rank 1 theories. Again, the combinatorial data allows to identify the singularity, and the monopole formula allows to compute exactly what are the properties of the symplectic singularity. Okay, I think I'm done here. There are many examples in physics, but I'm not sure this is the right audience to talk about them. Unless you insist, I will tell you about them. But there are applications in 5 dimensions, 6 dimensions, 4 dimensions. And we can go over them one by one. So let me summarize. Okay, I'm just flashing some of the computations that we are doing. And let me go to the summary. Coulomb branches, we call them magnetic weavers, and they are encoding all of the data needed to understand symplectic singularities. Hasse diagrams, we saw some of them as we went. This is an example of Hasse diagram. And here are some more Hasse diagrams, those diagrams here. They character, or we saw that in the case of the affine G2, affine Grassmannian. They are an important tool. Actually, we pretty much introduced this tool of the phase diagram to study symplectic singularities. And we do it in an intensive way through something which was mentioned before, quiver subtraction. Brain systems are very instrumental in all of the studies that we are doing. And the monopole formula is the key to have all of this progress. So thank you very much.